All right, I thought today we talk a little bit about the technique of rotary evaporation and how that applies to the organic chemistry lab and how it works. So let's start by pointing out that organic chemists often need to remove solvent from solute to collect their products. So let's say that we have a reaction mixture, and the solute, of course, is of interest to us. But the solvent, once it's served its purpose, we'd like to get rid of that so that we can go on with our analysis. So we need to do this when we use liquid-liquid extraction techniques. There's also a need when we're dealing with chromatography fractions. And as I've already mentioned, reaction mixtures, sometimes we want to get rid of that solvent and leave behind the non-volatile materials so that we can continue our work. So the question today is, how do we separate non-volatile solutes from volatile solvents? And the answer is rotary evaporation, which is basically a fancy type of distillation. So let's think a little bit about what a rotary evaporator is and how it works, and then we'll watch one in action at the very end today. Okay, so let's begin to familiarize ourselves with the rotary evaporator. I've shown a schematic here of a typical rotary evaporation unit, and I'm going to place this rotary evaporator next to a very familiar glassware apparatus from our labs, and that's the simple distillation apparatus. Now, while they may look quite different, there are regions of each which serve similar purposes. For example, they both have a boiling flask in which heat will be applied to try to drive volatile materials into the vapor phase. There'll be a condenser, which is an actively cooled region of glassware intended to condense that vapor back into a liquid. And then a receiving flask, a separate area of the apparatus where that condensed liquid accumulates to keep it separate from the original sample. So now that we've looked at some similarities here, let's go all the way through this rotary evaporator and identify all of the essential parts and what they do. I'll be referring to the round bottom containing your sample solution as a boiling flask. There's also a rotational unit, which is basically just a motor that spins that stem of the boiling flask right along the axis that goes through the opening. And we'll talk about why we do that in a little bit. There's also an elevation rail that allows you to slide the entire system up and down to put it into or raise it out of the baths that we're just about to talk about now. There's a Dimroth condenser, and a Dimroth condenser refers to that really cool spiral condenser that's inside of the glassware. And what that spiral cooling column does is creates a really large amount of cold surface area. So it's a very efficient condenser, and we need that for rotary evaporation to work. There's always a port for attaching a vacuum line, and of course ports for water lines as well, so that we can cool the condenser. What would be the receiving flask in a distillation is often referred to as the solvent trap, implying that we're catching the solvent and trapping it away from what we're really interested in, which is the residual non-volatile material in the boiling flask. There's a warm water bath used to encourage evaporation in the boiling flask, and an ice bath which is used to discourage evaporation once the solvent has begun accumulating in the trap. And of course there are controls for rotation and temperature. Now in other schematics you may see something called a bump trap, which is located between the boiling flask and the stem of the rotation unit. And the purpose of a bump trap is that if your sample does flash boil and goes up into the stem, it will now become contaminated, of course, with all the other junk that all the previous students have left in that stem. And the bump trap is a small bubble of glass designed to catch that liquid so it doesn't drain back into your flask and contaminate the material that you're trying to isolate. What's not optional, though, is you're going to need some Keck clips to be sure that you hold the solvent trap and boiling flask in place. You'll notice that in this particular diagram, without the clips shown, it's basically just a battle between gravity and the friction of those ground glass joints. And if your sample is heavy enough, gravity's going to win. You'll hear a splash, and you'll be starting over again because your boiling flask is now in the water bath. So be sure that you have the clips on hand to properly secure both of these flasks to the system. So now that we're really familiar with the rotary evaporator, let's talk about how we're going to use it. Let's take a quick run through what it looks like to have a rotary evaporation take place. Vacuum and water lines are commonly pre-attached. Most rotary evaporators are very large and you don't move them around very much, and therefore they tend to have dedicated vacuum and water lines. But if not, you'll need to apply those yourself. Now, before we start anything, we're going to inspect all the glassware that we'll be using, including the condenser, the solvent trap, the boiling flask, and the stem of the rotation unit. If there are any irregularities like cracks, stars, or chips, any defect in the glass which goes beyond just the surface into the matrix of the glass, then the rotary evaporator needs to be taken out of service because there's a significant risk of implosion if there is a weak point in any of the glassware that's being used. So once we've done our pre-check and we're ready to go, we run cold water to the Dimroth condenser. So this creates a zone of cooling in the condenser. We can also add some ice to a bath around the solvent trap if we want to be sure that we accumulate as much solvent as possible in the liquid phase and not allow it to vaporize back into the system. The next step would be to clip the boiling flask in place with your sample in it. So I've shown the sample inside of the flask, but I haven't explicitly shown the clip. It should be understood that it's there holding that flask in place. This way I can let go of that flask with my hand and begin the rotation. Rotation serves two purposes. First, it spreads some of the solvent out along the interior walls of the flask, promoting evaporation. Second, it agitates the sample slightly, which reduces the risk of bumping or flash boiling, which can cause solvent contamination or otherwise adversely affect your rotary evaporation. In the next step, we'll slowly evacuate the system by opening the vacuum line. And as we do that, you can see that the sample is now being agitated and it's now under reduced pressure, which means that the boiling points of all the volatile materials have been reduced. Finally, we're going to apply heat to that round bottom flask. So now we have our sample being agitated to prevent bumping, drawn onto the walls of the flask to encourage evaporation, evacuated, which encourages evaporation, and being heated, which encourages evaporation. So we've done everything possible to get all the volatile material to go into the vapor phase. So let's watch what happens when that actually takes place. As you can see, the volatile solvent materials are vaporizing, moving up the stem, condensing on the Dimroth condenser. From there, the liquid drains into the solvent trap until we've exhausted all the solvent from our sample. At this point, I've successfully isolated the volatile material from the non-volatile material in my solution. I can simply reverse the process of starting the rotary evaporation as a means of shutting it down. And once I'm done and the vacuum is quenched, I can remove my flask and begin working with my non-volatile material. So this is how rotary evaporation works.
إن أعجبك الفيديو لا تنسى الاشتراك بالقناة والإعجاب والتعليق على الفيديو، وأيضا لا تنسى المشاركة. جميع الحقوق محفوظة لقناة Arab Doctors Tube.